So now let's use complex numbers, which we're imagining we just freshly invented, and complex exponentials to solve a specific case of our core motivating problem, uh, damped oscillations. So here we have a mass on a spring. The mass, just for convenience, is 1 kilogram. The spring constant is 13 newtons per meter, and the damping constant is 4 newton seconds per meter. So here we are, written all out at the SI units. So we know that our guess, the super cool thing about this is by going to the trouble of inventing a whole new number system, we made it really easy to solve this. Which is kind of, maybe a little roundabout, but it's worthwhile. It just means that the guess was still, our original guess that started in way back in problem 1 still works. Y equals e to the alpha t works. Okay, and when we plug it in, we of course discover, let's just do that again. And again, if you really want to get anything out of this that you're going to retain and remember, stop the video and do this yourself and only start it again if you're really stuck. Oh, 13 e to the alpha t. Okay. So that means that this is a common factor, or the e to the alpha t is a common factor. We cross it out, and we just discover that the mystery alpha must satisfy this quadratic. Okay. And so let's see, quadratic formula. Actually, let's just complete the square. What the heck? It's really, I made it easy. Alpha squared, alpha plus 2 quantity squared. Well, that has a plus 4, so subtract 4. Oh, look. Alpha plus 2 squared equals minus 9. And of course, this is a plus. And of course, that's where we would have gotten stuck before, but now we realize that's plus or minus 3i. Okay? And again, the point I want to just harp on is that we're not just going to sit on that. We're going to use it, and it's going to come back to real numbers eventually. Okay, let's scoot it in over here. Alpha equals minus 2 plus or minus 3i. Okay, and we get 2, of course, and that's going to produce 2 viable guesses, and we're going to combine them with linearity. Okay, so this is almost finished with part A here, which is actually part of A and B, well, and starting part B. Okay, it's going to be some multiple of minus 2 plus 3i all times t, and then e minus 2 minus 3i all times t. Okay, so that's beautiful, but it doesn't fully wrap up the story that I want to tell, because again, my point at the start was we don't want to say we invent complex numbers and then we just say, oh, that's pretty, and just stare at it. I don't want to diss complex numbers at all, but the first time or first 100 times you use them, you should be able to say, what does this mean in terms of real functions? And of course, for our physical example, we desperately need real answers, or else it doesn't make any sense. Okay, so of course, to make this more explicit, we need an initial condition. So let's just look at one of the simplest non-zero initial conditions, pure motion, pure position information. We just stretch the spring out. We stretch it 1 unit past its equilibrium and let it go from rest, which is what this has. Okay, and this isn't going to be super special. It's just relatively simple. Okay, so, well, we can figure that out. Well, first thing we need to write down is what's y prime of t. But that's easy, of course, as long as we're okay with a little bit of complex number arithmetic. And then the C2, and then that's minus 2 minus 3i. Okay. And now we can plug in the zeros. Okay, y of 0 equals 1. When you plug in y of 0, boom, that's 1, that's 1. And so we get a pretty simple equation. C1 plus C2 equals 1. This one's going to be a little more complicated. This says C1 times minus 2 plus 3i plus C2 times minus 2 minus 3i equals 0. Okay, so we need to solve that. Alrighty, well, we could make it into a matrix, we could do elimination, whatever. Yeah, let's do elimination. Okay, let's go ahead and multiply both sides of this by, let's say, minus 2 minus 3i. Minus 2 minus 3i C1 plus minus 2 minus 3i C2 is minus 2 minus 3i. Oops, not quite fitting. Okay, and now I'm going to subtract this equation from this one. Okay, and so we're going to get um, the minus 2's cancel, and we're going to get minus 6i c1 equals, now these guys go away completely, equals minus 2 minus 3i. Okay, and so c1 is minus 2 minus 3i over minus 6i. We can simplify that. Scoot it up a little bit. Okay, so the minuses and signs all cancel. Now dividing by I, it's the same thing as multiplying by minus I. And so we get minus 1/3 I plus 1/2. Okay. Alrighty, so there's the C1. And then C2 is just 1 minus that. And we're going to discover something interesting. You might want to stop and guess, or if you've ever done this before, you might remember what's special about the relationship of C1 and C2. So C2, well, let's just write down C1 again. C1 is 1/2, we'll write in the standard order, minus 1/3 I. C2 is 1 minus that, and so that's the 1/2 stays the same, and then this just flips. If I take 1 minus a half, it's a half, and 1 minus the minus that flips that guy. Well, what do you notice about C1 and C2? C2 is C1 bar. Okay, and I claim that's not at all accidental. Okay, because we know that if we start out with real numbers here, there's absolutely no reason why the actual solution is going to be complex. We are going to get a real solution. This spring, this mass doesn't move into the imaginary dimension somehow in some magical way. Okay, and so how on earth would we get a real number out of the sum of two complex numbers? Well, when you sum two complex numbers and you get a real number, then these guys must be complex conjugates of each other, because the i's have to cancel out. And just a nice way to say that is they're complex conjugates of each other. Okay, now these guys are already complex conjugates of each other, because this is of the form e to the z, and this is an e to the z bar. Because notice, since t is a real number, because we haven't gone to imaginary time, which you do in some physics, but not here, this really is just the complex conjugate of this guy. Do you hear my cat scrabbling at the door? He just wants to be in this video, but I'm not going to let him. So these guys are conjugates of each other. That was something we talked about before. And so the only way that the whole things are going to be conjugates is if the C1 and C2 are conjugates. So that actually, if we'd observed that first, there would have been a slicker route to figuring this out. But I wanted it to kind of show up on its own. Okay, so far we've just got a very explicit thing, but still talking about complex exponentials. Yeah, my cat just really wants to be part of the action here, but he would just mess things up. He would actually stand on the keyboard. Okay, so are we done? Well, if you really love complex exponentials, this is not a bad place to be. But, of course, the goal was to get something in terms of real functions. Okay, so this is a good place to observe, to use that fact. We can do this a couple ways. We can just expand everything out. We really need to get the cosines and sines coming out of here. And we could just expand everything out. It's a little more clever to realize, again, that this is some number plus its complex conjugate. So this is just 2 times the real part of that whole thing. That's just slightly slicker, okay? But we still need to figure out what that is, okay? So I'm just going to get the real part. Now, e to the minus 2t comes out as a factor, okay? And then what is this going to be? I'm going to get I'm going to get cosine 3t plus I sine 3t. And I'm just going to drop the part so it's going to have an imaginary. So I'm going to have 1/2 cosine 3t. And then the other part is going to be the minus 1/3 I times the sine 3t times I sine 3t. The minus sine I cancel, and I get plus 1/3 sine 3t. If that's a little too quick, then a good place to do it yourself. Okay, and I'm just going to drop the real part because I actually just did in the head go ahead and bother about the imaginary part. So there you go. So just, I don't know, we'll leave it like that. The 2 can be factored in. Let's do that. This looks prettier. And so 2/3. There we go. So what do we get? We get an exponential times oscillation. Oh, that's exactly what we're seeing in that applet. We start out like here, and we have damped oscillations. This is going to be some sort of shifted and scaled sine wave, and then it's times exponential damping. And so it's going to look like this. And that's exactly what we saw with the applet. And that's what we expect physically from a spring with some damping. Some oscillation and then damping. Okay. So we've really figured out a method for solving these problems. And in the next video, I'm going to finish up, I think it'll be our last video, by talking about a little bit more of a little more sophisticated way, the power of this. And again, the idea was not so much solving a particular problem, is having a unified method for solving all these problems. That said, this is still the best method for even solving this one problem, because this is, yeah, it's kind of guessable, but it's kind of messy, and it's very slick to do it this way. But where we get the real full power is where we look at a family of functions, a family of equations, and so you should look at that on the PDF before you start the next video.